welcome to the deep dive. Today we're tackling, well, maybe the ultimate question in science. What is reality, fundamentally? We're going to explore this through the really strange history of light and dive deep into quantum mechanics, using insights from sources like John Gribbin's work, which itself built on Schrödinger's famous cat paradox.
That's the plan. We're aiming to unpack some of physics' most notorious paradoxes for you. It's kind of a two-part mission, really.
Okay.
First, we trace that long historical fight over what light even is. And second, we look at the really wild modern ideas trying to make sense of the quantum world, especially the double-slit experiment.
Yes, the double slit. And you really can't start anywhere else, can you? Richard Feynman basically said it all comes down to this one experiment.
He did.
He said it contains the only mystery of quantum mechanics, and it's, quote, absolutely impossible to explain the classical way. And, when you hear the details, it makes perfect sense why he'd say that.
Right. So let's picture it simply first. Think about waves in water. If you have a barrier with two little slits, the waves pass through both.
And they ripple outwards from each slit.
Exactly. And those ripples interfere with each other. Where crest meets crest, you get a bigger wave. Where crest meets trough, they cancel out.
So on a screen, behind the barrier, you get this pattern of stripes, right? Bright and dark bands. Classic wave behavior.
Precisely. That's the interference pattern. Totally normal for waves.
Okay, but now, the quantum part. You do this with electrons, which are definitely particles, right? They have mass, charge.
Undeniably particles. But get this. When you fire electrons one by one through the two slits, you still end up with that same interference pattern on the screen.
Wait, even firing them one at a time? How does one electron interfere with itself?
That's the mystery. It seems each electron somehow travels like a wave, goes through both slits simultaneously.
As a wave?
As a wave. But then when it hits the screen, boom, it arrives as a single localized particle, one dot.
Okay, so it travels like a wave but lands like a particle. Weird, but maybe manageable. Until
you try to find out which slit it actually went through.
Right, the observer problem. This is where it gets truly mind-bending. You set up a detector, maybe the tiny light beam, by one of the slits to see the electron pass.
And the moment you do that, the instant you try to observe its path, the whole game changes.
The interference pattern
It just
vanishes.
completely gone, instantly. What you see instead is just two distinct clumps of dots on the screen directly behind each slit.
Like you're just firing tiny bullets through. No wave behavior at all.
Exactly. It's as if the electron knows it's being watched and decides, okay, act like a particle now. The very act of measuring forces it to choose a single path.
Which directly connects to things like Schrödinger's cat, doesn't it?
It does. The cat isn't definitively dead or alive until you open the box and observe it. Before that, it's in a superposition, a blur of both possibilities.
The observation itself seems to, well, create the reality we see, which is deeply unsettling.
Yeah, and it helps remember this whole particle wave confusion isn't new. The argument over light goes back millennia. Some early Greeks, like Empedocles, didn't even think light came to the eye.
They thought it shot out from the eye, like little searchlights.
Sort of, yeah. Probing the world. Fast forward quite a bit, and you get Isaac Newton. Huge figure, obviously.
And he was firmly in the particle camp. Corpuscles, he called them.
Yeah, little particles of light.
Right.
It fit beautifully with his laws of motion, his mechanical universe, and his work with prisms, splitting white light into colors.
That seemed to seal the deal for particles, didn't it? His authority carried it for, what, a century?
Pretty much through the 1700s, yeah. But there was a snag in the particle theory, a prediction it made.
About speed.
Exactly. To explain refraction light bending when it enters water, or glass, Newton's particle model actually required light to speed up in denser stuff.
Which feels wrong. And turns out it is wrong.
It is. And that opened the door for the wave theory to make a comeback, thanks mainly to Thomas Young.
Young and his version of the double-slit experiment, right? Using light this time.
Yes. He showed light definitely creates interference patterns, just like water waves. Proof of wave behavior. He even calculated the wavelengths incredibly tiny.
Like fractions of a millionth of a meter.
Tiny. Which explained why you don't normally see light bending around corners easily, why the particle idea seemed so intuitive before. The wavelengths are just too small for everyday effects.
Okay, so Young gives wave theory a huge boost. But the final nail in the particle coffin, for a while anyway, was almost accidental.
Kind of, yeah. It involved Augustin Fresnel and his really advanced math for wave diffraction. a skeptic, Simeon Poisson.
A Newtonian, a particle guy.
Right. Poisson used Fresnel's own wave equations to predict something he thought was totally absurd.
He calculated that if Fresnel was right about waves, there should be a bright spot right in the middle of the shadow of a perfectly round object.
Exactly. Sounds ridiculous. A bright spot in a shadow. He thought it would disprove the wave theory.
But then they did the experiment.
And there it was, the Poisson spot. A tiny, bright dot exactly as Fresnel's wave math predicted. It was a stunning confirmation. Common sense said no, the math said yes, and nature agreed with the math.
So wave theory wins. For now.
For then, yes. And this set the stage perfectly for James Clerk Maxwell in the 1860s, building on Faraday's idea of fields.
Invisible fields filling space.
Maxwell unified electricity and magnetism, 4 elegant equations, and out popped light automatically as an electromagnetic wave traveling at a specific speed, c.
And crucially, that speed c came just from electrical and magnetic constants, not from anything about light itself.
Correct. It showed light was an electromagnetic phenomenon, and its speed was baked into the laws of electromagnetism itself. A triumph for wave theory. Tag 3, relativity, quanta, and the crisis of the ether.
Okay, so light's a wave traveling at c, but c relative to what? That was the next big question, right?
Uh-huh. The assumption was this invisible medium, the luminiferous ether, filling all space. Light waves supposedly waved through this ether.
Like sound waves through air. Makes sense. So
Except nobody could find it. The Michelson-Morley experiment in 1887 was designed specifically to detect Earth moving through this ether.
by measuring tiny differences in the speed of light traveling in different directions relative to Earth's motion.
Precisely. But they found nothing. No difference. The speed of light was the same no matter which way they looked or how the Earth was moving.
Which was a huge crisis for physics. If
Yeah.
there's no ether, what is light waving in? And why is its speed constant?
Enter Albert Einstein, 1905. Special relativity.
Yeah.
He just threw out the ether entirely.
Bold move.
He proposed that the speed of light c isn't constant relative to some ether, it's constant for all observers, period. It's an absolute cosmic speed limit.
And to make that work, our ideas of space and time had to become flexible, intertwined space-time.
Exactly, a complete revolution. But just as wave theory seemed totally supreme, thanks to Maxwell and Einstein, physics took another sharp turn.
Back towards particles.
It started with Max Planck in 1900, looking at black body radiation, basically, how hot objects glow. Classical physics predicted they should emit infinite energy at high frequencies, the ultraviolet catastrophe.
Because obviously it doesn't happen. You don't get blasted with X-rays every time you turn on a stove.
Right. Planck found he could fix the math only if he assumed energy wasn't continuous but came in discrete packets, or quanta.
Energy chunks. Okay, that's weird, but maybe just a mathematical trick.
That's what Planck thought initially, but then Einstein and later Satyendra Nath Bose took it much further. Einstein proposed that light itself is made of these quanta particle-like packets of light energy.
Photons.
Photons. So after a century of wave dominance, the particle was back. Not corpuscles exactly, but discrete energy packets. This kicked off the whole development of quantum mechanics, wave mechanics by Schrödinger. It's this constant back and forth, particle, wave, both. Tag 5e, interpretations, and non-locality.
Okay, so now we're stuck with this wave-particle duality. An electron is somehow both, depending on how you look. And Heisenberg's uncertainty principle tells us you can't even know both its position and momentum precisely at the same time.
Right. The fuzziness is fundamental. It's not just about our measurement limitations. The properties aren't sharply defined until measured.
Which leads us to maybe the strangest part, non-locality. John Bell figured out a way to test these ideas.
Bell's theorem, yeah. It set up a testable difference between standard quantum mechanics and theories, assuming reality is local, meaning effects can't travel faster than light.
And the experiments, like Elaine aspects.
They came down firmly on the side of quantum mechanics. They confirmed what Einstein hated. Spooky action at a distance.
Meaning you can have two particles created together and sent far apart.
Entangled particles, yes.
And if you measure a property of one, say its spin, you instantly know the spin of the other one, no matter how far away it is, faster than light could possibly travel between them.
Instantaneously. That's non-locality. The correlation is immediate.
So what does that mean? Either information is traveling faster than light, breaking relativity, or the two particles aren't truly separate, or reality itself isn't fully real until measured.
Those are the tough choices it forces on you. It shatters our intuitive sense of space, time, and causality, and the standard interpretation, the Copenhagen view.
It basically says, shut up and calculate, right? Don't ask how the measurement collapses the wave function. Just accept that it does when an observer gets involved.
Pretty much, but it leaves that measurement problem dangling. What counts as the observer? The detector, the computer, a human mind. Does a cat observing itself count? It gets philosophical fast.
Okay, so if Copenhagen is unsatisfying, what else is there? You mentioned a modern idea. Transactional interpretation.
Yes, John Kramer's idea. It's a really interesting way to think about it using time in a novel way.
How does it work?
It pictures a quantum interaction, like light traveling from A to B, as a handshake. The emitter A sends out an offer wave forward in time.
Okay.
And the potential absorber B sends back a confirmation wave backward in time.
Whoa, backward in time? Seriously?
From our perspective, yes. But think about the photon itself. For something traveling at light speed, according to relativity, time essentially stops. 0 time elapses between emission and absorption from its point of view.
So the offer and confirmation are instantaneous.
Effectively, yes. The whole transaction happens at once outside of our usual flow of time. This handshake establishes the quantum event.
And how does that help with non-locality, the spooky action?
Because if the connection, the transaction, is fundamentally timeless, then the correlation between entangled particles isn't spooky action at a distance, it's part of a single timeless event. The separation in space is irrelevant because the connection isn't limited by the speed of light in the usual way.
So it resolves the paradox by stepping outside our normal concept of linear time. That's a big step. Hashtag V, physics, models, and analogy, meta-reality check.
It is. And thinking about these kinds of interpretations makes you reflect on how physics even works, how we talk about things we can't directly see.
We rely so much on analogy, don't we? Comparing atoms to solar systems, even though we know it's wrong. I read physicist Nick Herbert felt like a cheat drawing that model.
Exactly, because all our models, billiard ball atoms, solar system atoms, electron clouds, they're just that. Models, tools. They're useful for explaining certain things, for making predictions, but they aren't the thing itself.
We can only know what reality is like using the analogies we have available.
Right, and sometimes the analogies loop back on themselves, like explaining forces between atoms using the idea of tiny springs.
But the spring itself is made of atoms held together by the same kinds of forces.
Precisely. So the analogy becomes electromagnetic forces are like, well, electromagnetic forces. It shows the limits of mapping everyday concepts onto the quantum realm.
Which leads to this deeper idea from thinkers like Andrew Pickering. Maybe things like quarks aren't just discovered, but are partly constructed by the way physicists choose to investigate, by the models and analogies they pick.
It's a challenging thought, that the reality we describe is intertwined with the practice of doing physics. Martin Krieger talked about physicists choosing handles on a complex system.
Handles, like simplifying.
Yeah, like studying a gas. You ignore the zillions of individual molecules whizzing around. You wait for it to settle down, reach equilibrium, and then you grab onto one simple handle temperature or pressure.
So the description of the model depends entirely on what aspect you choose to focus on, what handle you grab, and what complexity you decide to ignore.
It suggests our scientific picture of reality is always going to be a particular perspective, shaped by our methods and choices, not necessarily the one absolute total truth of the matter. #Howtro.
Okay, so we've traced this incredible journey from ancient ideas about light through the centuries-long battle between particles and waves,
culminating in the quantum weirdness where light and matter seem to be both and neither until we look.
And we've seen how our definition of reality seems tied to the models we use, especially when dealing with quantum effects like non-locality.
Yeah, and that transactional interpretation really stands out as a way to potentially resolve these deep mysteries. It provides a consistent story.
But at a cost. We have to accept that quantum interactions might happen outside of time, or in a way that involves communication both forward and backward in time.
Right. It suggests that our everyday experience of time, cause always preceding effect, might be just an emergent property of large-scale complexity, a kind of pseudo-time.
Whereas the underlying quantum reality operates on a different, possibly timeless framework.
A timeless handshake across the universe, completing instantaneously from the photon's perspective.
Which leaves you, our listener, with a pretty profound thought to chew on. If the basic level of reality operates outside of our linear time, if connections can be instant across vast distances, what does that mean for concepts like free will?
Our sense of making choices, of experiencing things sequentially, seems utterly dependent on time flowing in one direction.
Yet, as the physicist David Bohm noted, physicists deep down want to believe in an external world existing independently of us. But the quantum evidence keeps pushing back, suggesting observation isn't just passive viewing, but an active part of creating what is real. How independent is that world then, really? Something to think about.